Last hope, experiment finds evidence for unknown particles. Long-awaited news from Fermilab's muon G2 team may resolve a tantalizing conflict between nature and theory. But a separate calculation clouds the picture. Elementary particles crackle with the energy of virtual particles that constantly pop into and out of existence. Fermilab's muon G2 experiment has found strong evidence that the standard model of particle physics can't fully account for what's going on. 20 years after an apparent anomaly in the behavior of elementary particles raised hopes of a major physics breakthrough, a new measurement has solidified them. Physicists at Fermi National Accelerator Laboratory near Chicago announced on April 7 that muons, elementary particles similar to electrons, wobbled more than expected while whipping around a magnetized ring. Original story reprinted with permission from Quantum magazine, an editorially independent publication of the Simons Foundation whose mission is to enhance public understanding of science by covering research developments and trends in mathematics and the physical and life sciences. The widely anticipated new measurement confirms the decades-old result, which made headlines around the world. Both measurements of the muon's wobbliness, or magnetic moment, significantly overshoot the theoretical prediction, as calculated last year by an international consortium of 132 theoretical physicists. The Fermilab researchers estimate that the difference has grown to a level quantified as 4.2 sigma, well on the way to the stringent 5 sigma level that physicists need to claim a discovery. Taken at face value, the discrepancy strongly suggests that unknown particles of nature are giving muons an extra push. Such a discovery would at long last herald the breakdown of the 50-year-old standard model of particle physics, the set of equations describing the known elementary particles and interactions. Today is an extraordinary day, long awaited not only by us but by the whole international physics community. Graziano Venanzoni, one of the leaders of the Fermilab muon G2 experiment and a physicist at the Italian National Institute for Nuclear Physics, told the press. However, even as many particle physicists are likely to be celebrating and racing to propose new ideas that could explain the discrepancy, a paper published on the same day in the journal Nature casts the new muon measurement in a dramatically duller light. The paper, which appeared just as the Fermilab team unveiled its new measurement, suggests that the muon's measured wobbliness is exactly what the standard model predicts. In the paper, a team of theorists known as BMW present a state-of-the-art supercomputer calculation of the most uncertain term that goes into the standard model prediction of the muon's magnetic moment. BMW calculates this term to be considerably larger than the value adopted last year by the consortium, a group known as the Theory Initiative. BMW's larger term leads to a larger overall predicted value of the muon's magnetic moment, bringing the prediction in line with the measurements. If the new calculation is correct, then physicists may have spent 20 years chasing a ghost. But the Theory Initiative's prediction relied on a different calculational approach that has been honed over decades, and it could well be right. In that case, Fermilab's new measurement constitutes the most exciting result in particle physics in years. This is a very sensitive and interesting situation, said Zoltan Fodor, a theoretical particle physicist at Pennsylvania State University who is part of the BMW team. Electromagnets inside the 50-foot wide muon G2 ring must be cooled to just a few degrees above absolute zero. BMW's calculation itself is not breaking news. The paper first appeared as a preprint last year. Aida El Khadra, a particle theorist at the University of Illinois who co-organized the Theory Initiative, explained that the BMW calculation should be taken seriously, but that it wasn't factored into the Theory Initiative's overall prediction because it still needed vetting. If other groups independently verify BMW's calculation, the Theory Initiative will integrate it into its next assessment. Dominik Stockinger, a theorist at the Technical University of Dresden who participated in the Theory Initiative and is a member of the Fermilab muon G2 team, said the BMW result creates an unclear status. Physicists can't say whether exotic new particles are pushing on muons until they agree about the effects of the 17 standard model particles they already know about. Regardless, there's plenty of reason for optimism. Researchers emphasize that even if BMW is right, the puzzling gulf between the two calculations could itself point to new physics. But for the moment, the past 20 years of conflict between theory and experiment appear to have been replaced by something even more unexpected, a battle of theory versus theory. Momentous muons. The reason physicists have eagerly awaited Fermilab's new measurement is that the muon's magnetic moment, essentially the strength of its intrinsic magnetism, encodes a huge amount of information about the universe. A century ago, physicists assumed that the magnetic moments of elementary particles would follow the same formula as larger objects. Instead, they found that electrons rotate in magnetic fields twice as much as expected. Their gyromagnetic ratio, or G factor, the number relating their magnetic moment to their other properties, seemed to be 2, not 1, a surprise discovery later explained by the fact that electrons are spin -1/2 particles, which return to the same state after making 2 full turns rather than 1. For years, both electrons and muons were thought to have G factors of exactly 2. But then in 1947, Polycarp Cush and Henry Foley measured the electron's G factor to be 2.00232. The theoretical physicist Julian Schwinger almost immediately explained the extra bits. He showed that the small corrections come from an electron's tendency to momentarily emit and reabsorb a photon as it moves through space. Many other fleeting quantum fluctuations happen as well. An electron or muon might emit and reabsorb 2 photons, or a photon that briefly becomes an electron and a positron, among countless other possibilities that the Standard Model allows. These temporary manifestations travel around with an electron or muon like an entourage, and all of them contribute to its magnetic properties. The particle you thought was a bare muon is actually a muon plus a cloud of other things that appear spontaneously, said Chris Polly, another leader of the Fermilab muon G2 experiment. They change the magnetic moment. The rarer a quantum fluctuation, the less it contributes to the electron or muon's G factor. As you go further into the decimal places, you can see where suddenly the quarks start to appear for the first time, said Polly. Further along are particles called W and Z bosons, and so on. Because muons are 207 times heavier than electrons, they're about 2072, or 43,000 times more likely to conjure up heavy particles in their entourage. These particles therefore alter the muon's G factor far more than an electron's. So if you're looking for particles that could explain the missing mass of the universe, dark matter, or you're looking for particles of a theory called supersymmetry, Polly said, that's where the muon has a unique role. For decades, theorists have strived to calculate contributions to the muon's G factor coming from increasingly unlikely iterations of known particles from the Standard Model, while experimentalists measured the G factor with ever-increasing precision. If the measurement were to outstrip the expectation, this would betray the presence of strangers in the muon's entourage, fleeting appearances of particles beyond the Standard Model. Muon magnetic moment measurements began at Columbia University in the 1950s and were picked up a decade later at CERN, Europe's particle physics laboratory. There, researchers pioneered the measurement technique still used at Fermilab today. High-speed muons are shot into a magnetized ring. As a muon whips around the ring, passing through its powerful magnetic field, the particle's spin axis, which can be pictured as a little arrow, gradually rotates. Millionths of a second later, typically after speeding around the ring a few hundred times, the muon decays, producing an electron that flies into one of the surrounding detectors. The varying energies of electrons emanating from the ring at different times reveal how quickly the muon spins are rotating. In the 1990s, a team at Brookhaven National Laboratory on Long Island built a 50-foot wide ring to fling muons around and began collecting data. In 2001, the researchers announced their first results, reporting 2.0023318,404 for the muon's G factor, with some uncertainty in the final 2 digits. Meanwhile, the most comprehensive Standard Model prediction at the time gave the significantly lower value of 2.0023318,319. It instantly became the world's most famous 8th decimal.